So in today's reaction, here we are to deal about Markovnikov rule, one of the most asked question from Hello Alkane. Anti-Markovnikov rule, harsh effect, SN1 and SN2 reaction, dehydrogenation reaction, which is also known as elimination reaction. Inside that, we have a rule known as Sedgwick rule, Wurtz reaction, reaction of alkyl halide with NaNO2, KNO2, AgNO2, and the last one, reaction of alkyl halide with NaCN KCN, AgCN, and also with aqueous KOH and alcoholic KOH. So we'll be dealing it one by one. At the end, I'll be having some of the questions, so kindly visualize the entire video and make sure that you will be able to solve the question attached at the end. If you will be able to do so, kindly attach it in the comment section. So, what exactly is Markovnikov rule? Markovnikov's rule. So, this is basically for unsymmetrical alkene. So, what exactly is unsymmetrical alkene? Unsymmetrical alkene. So unsymmetrical alkene, if you are adding an unsymmetrical reagent like HCl or HBr, if I need to add it out. So basically, what will happen is, according to Markovnikov, so if I have an unsymmetrical alkene, let me take an example of unsymmetrical alkene like CH3, CH double bond CH2. So what you can visualize right in this is this C on the either side of the double bond. Here you have only a CH2 group and here you have a CH3 and a CH. So on the either side of a double bond, this carbon has only one hydrogen, whereas this carbon has two hydrogen. So the rule says that hydrogen, this HBr, when it dissociates, then into plus and minus charges, and if the situation will be like one of the bond will break and one of the atom, one of the carbon will have a, obviously it will have a positive charge and the other will have a negative charge. So right in this scenario, what will happen is according to Markovnikov rule, what it says is hydrogen attaches to the carbon having more number of hydrogen. Hydrogen will attach in a carbon which have considerably more number of hydrogen, and bromine will go and attach to the carbon having less number of hydrogen. So the product those formed will be CH3, CH having single bond, and this will again turn to be CH3, and the Br will attach right in carbon number 2 in order to give 2 bromopropane. So basically what it says is hydrogen attaches to the carbon having more number of hydrogen. Okay, so what exactly, if I have, let me take some other example. If I have something as such CH3, CH2, CH2, double bond, let me make it CH, CH, double bond, CH, and then there will be CH3. So in this case, what exactly is there is, it is not an unsymmetrical alkene. Why am I saying so? Because right over here on the either side of the double bond, here this carbon also contain one hydrogen and this carbon also contain one hydrogen. So at this situation, basically the hydrogen can attach with any of the carbon because either of the carbon has one hydrogen. Then, so hydrogen can attach right to this as well and on the other side. So basically Markovnikov rule is for unsymmetrical alkene. This is basically for unsymmetrical alkene. Okay. Now let's move on for anti-Markovnikov rule. Let's move on for anti-Markovnikov rule. That is our number two. Anti-Markovnikov rule, or we also call it Kars effect. We also call it Kars effect or anti-Markovnikov rule. So basically, what you need to remember is anti-Markovnikov rule is only for if this is only for HBr. If we have any other thing to be attached other than HBr, so the reaction will not take place. If we have HCl, if we have HR, if we have HF, so HI, sorry, at the time, this will not go for. So anti-Markovnikov rule is only for HBr and it takes place only in the presence of peroxide. The reaction takes place only in the presence of peroxide. If there is no peroxide, so if there is peroxide, hydrogen peroxide or presence of peroxide, okay. So the reaction for necessary condition for reaction is there need to be HBr and there need to be peroxide. Only then the reaction takes place. So we also name it as peroxide effect. Sometimes we also call this effect as peroxide effect. Peroxide effect. Again, what will happen is, in this also will have an unsymmetrical alkene. Like if I have CH3, same condition, CH, double bond, CH2. And here I have HBr. Then, and what exactly is the situation is, I need to give the product in the presence of peroxide. Mean there I have peroxide. So there we have peroxide. So basically what will happen is, in this one, the condition is just opposite of that of Markovnikov. Markovnikov was saying that the hydrogen will attach to the carbon having more number of hydrogen. But anti-Markovnikov says that hydrogen will go and attach to the carbon having lesser number of hydrogen. So hydrogen will move to the carbon having less number of hydrogen, whereas bromine will move to the carbon having more number of hydrogen. So that the product formed will be CH3, CH2, and there will be CH2 and Br. Whereas if there is no peroxide, if I have no peroxide, so the product will be reversed again. At this condition, the product will be something else. That is, the product will be CH3, CH, CH3, and here will be your Br. So this reaction took place in the presence of peroxide, and the second reaction is taking place in the absence of peroxide. This reaction is taking place in the absence of peroxide. So if there is peroxide, hydrogen will attach to the carbon having less number of hydrogen. And if there is no peroxide, hydrogen will attach to the carbon having more number of hydrogen. So and this effect is known as, or this rule is known as anti-Markovnikov rule. And here the product forms are different. This one is what we call as 1-bromopropane, and this one is what we will call it as, 2-bromopropane, and we'll call it as 1-bromopropane. So that is what we are going to do. Let's move on for the third one that I marked, I believe, is SN1 and SN2 reaction. I think I have listed it above. The third one that we need to do is SN1 and SN2 reaction. So what exactly is SN1 and SN2 reaction? So first let's be clear about what is SN over there. SN1, or we also call it substitution nucleophilic unimolecular reaction. Substitution nucleophilic unimolecular reaction. So basically, what is substitution? Let me make you clear. Substitution means one of the atom from the given reactant will be removed, and instead of that, a nucleophile will be taking place of it. What will happen is, there will be a given compound. You will have a reagent right there. Like if I have a compound that is CH3, C, H, H, and here I have Br. So what will exactly happen is the Br will leave the place, and instead of Br, I will have a nucleophile like OH minus, which will right take its place. So we'll call it substitution nucleophilic reaction or nucleophilic substitution. Here it says nucleophile. nucleophile, and this is my substrate. And here I have a product that is CH3, H, H, and here I have OH group. So this one is the product, and along with this, what will come out is Br minus. Okay. So now let's move on for what is SN1. This is specifically only substitution reaction. Now let me explain you what is substitution nucleophilic unimolecular. Okay. So now let's get inside SN1, HN1 reaction. So let me make you clear. It is SN1 reaction. So SN1 reaction will be taking place in two steps. From the name itself, you can be very clear. This reaction takes place in two steps. SN1 means two step, SN2 means one step. Okay. Here, what will happen is first there will be dissociation. First, first there will be dissociation, and then, and in the second step, there will be association. So first dissociation and then association. So this is gonna take, let's take an example and then we'll make you understand. Step one. What will exactly happen in this is we have a nucleophile, we have a substrate like CH3, C, CH3, CH3, and here you have a Br group. And what will happen is in the first step, this will break down, the bond will break, and it will form something like this C, having three CH3 group attached to it, and the carbon will have a positive charge in it. And on the other side, there will be Br having minus charge in it. So what we can observe is first there is dissociation, and in the step two, this one is a slow reaction, a slow speed. The speed of reaction is slow comparatively. Second, what do I have is again I have the same substrate CH3, 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 and here I have a plus charge, and the other side I have another nucleophile which will take its place. And this is comparatively the step is fast. So now what will happen is this nucleophile will go and attack it in order to form the product like C. Three of the CH3 groups are there, and instead of Br, now there will be OH. So what exactly happened is the Br has been substituted by the OH group. Here, first dissociation took place and then association. In the first step, what we have is dissociation, and in the second step, what we have is association of nucleophile. So this reaction, basically, what you might have known about is the rate of reaction depends on the slow state. You might be already clear about this. The rate of any reaction always goes for the slow state. So here the rate only depends upon the rate of reaction only depends upon the concentration of this substrate. It doesn't have any link with this nucleophile. It doesn't have any connection. The rate depends only on the substrate. So rate basically is only dependent on your substrate. Rate of reaction doesn't have any relation with the nucleophile. Hence, it is known as HN1 reaction. Okay. So what you need to remember is SN1 is double step reaction. First, there will be dissociation. Second, it will be association. In SN1 reaction, the rate depends only on the substrate. Hence, it is known as SN1 because it is only dependent on the substrate. Okay. Now, let's move on for SN2 reaction. What exactly is SN2 reaction? SN2 reaction. What is SN2 reaction? So SN2 reaction is single step reaction. What you need to remember, it is single step reaction. So the reaction will take place in single step. Next, there will be first association, and then dissociation. So in the first step, there will be association, and the second step, there will be dissociation. So what is basically happen is, if I have a nucleophile like something, H, 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 and Br right there, and there I have a nucleophile like OH minus. So what will happen is, a partial, because it's more electronegative, so there will be a partial negative charge and there will be partial positive charge. The nucleophile will come and attack. This is your nucleophile. Then the situation will be something like this. C having three of the H group right there, and remaining Br, and here I have OH at the same time. So again, this one will be a slow step, and the final step what will be there is, now the bond will break, this bond will break, and the situation will be something like this. There will be the formation of C, H, H, and H, and here will be your OH group along with the liberation of Br minus. So here the rate is dependent on either of the thing. It is dependent on substrate as well as nucleophile. So rate is dependent on both substrate and nucleophile, hence we call it SN2 or substitution nucleophilic bimolecular. So the reason behind calling it SN2 is because rate is dependent on substrate and nucleophile both. And in the above it was only called SN1 because the rate was dependent only on the substrate. Okay. In SN1 it was double state. There was first dissociation and then association. In SN2, it is single state. There will be first association and then dissociation. So these are the common factors. Now let's move on for dehydrohallucination reaction. What exactly is the dehydrohallucination reaction? Let's move on for that. Dehydro, so hallucination reaction. So a hydrogen and a halogen is being replaced right there. So what will basically happen is, if I have a R group, and if there is carbon having two of the hydrogen and the other carbon again having two of the hydrogen and a halide group, let me consider it as a X. X can be any of the halogen. Okay. And if I'm reacting it with alcoholic KOH, potassium hydroxide, but in alcoholic solution, the solvent need to be alcoholic. If I have this scenario and slightly hitting it, what will exactly happen is, this hydrogen will take this halogen in order to form it hydrogen halide, or this K group. This one will break as K plus and OH minus. Then this OH minus will be taking it right as OH and H will together form H2O, and K will go with X to form KX potassium halide. And this either of the bond will break. So what will exactly happen is, this bond will move slightly over here in order to form it alkene. So from alkane to alkene, there will be the transformation. That is, the scenario will be something like this. There will be R, there will be C and H, there will be C and H2. But here, the second bond will be double bond. When here it was hydrogen halide or haloalkane, and here it turned into alkene. So what you basically need to remember is if you treat an haloalkane, right, with an alcoholic potassium hydroxide. So this is what you need to know. Alcoholic KOH. Only in the presence of alcoholic KOH, dehydrohalogenation reaction takes place. One of the hydrogen and one of the halogen has been replaced or removed. Hence, it is known as dehydrohalogenation reaction. And what it exactly formed as an alkene. Let's move for the next one. Inside this, again, they generally have an confusion. Student basically create some confusion in Sajjaf rule. So what exactly is Sajjaf rule? Let's know about this. Sorry. Sajjaf rule. So in Sajjaf, what about Sajjaf rule basically speaks as sometimes the degree of hydrogen can be different. Let me explain you with an example, and even you people will, I think, will be able to explain the thing. So here I have CH3 group, again a CH2 group. Next I have a carbon, again a CH3 attached with it, again a CH3 attached with it, and here I have a halogen. Okay. And I'm treating it right with, in this either of the condition, I'm treating it with alcoholic KOH. So I'm treating it with alcoholic KOH. So no doubt we are very much clear that the reaction will be dehydrohalogenation reaction because there is a have alcoholic KOH and we are treating it with alkyl halide. Okay. Now the point of concern is where you generally have confusion is here you have a bromine group, right? And the bromine can go or bromine can dehydrogenate with on the either side of this carbon. Here also there is a carbon containing hydrogen, and here also there is a carbon containing hydrogen. So, if this bromine will take away a hydrogen from this carbon, the product will be something like this. Let me explain you. The product will look like CH3, CH2, C, CH3, double bond, CH2. So what happened in this case is this bromine and one of the hydrogen from last carbon has been removed. Whereas if it happens something like that the this bromine and a hydrogen from this carbon, the third carbon has been removed. So what's a situation or what type of answer I'll get at this point is CH3, C. If one of the hydrogen from this carbon will be removed, it will be CH. And here there will be double bond. And here I will have C, CH3, and here will be CH3. So the two of the alkene that we are visualizing right now is not same. Basically, I'll call them, for the first one, I'll name it as 2-methyl, 2-methyl but 1-ene, and the second I'll be naming it as 2-methyl but 2-ene. So the product in this case is not same. Now, according to Sedgwick's rule, the first one will have a lower probability of formation. Basically, this one will only be 29%, formation will be only 29%, and the other one will be 71%. So what basically Sajjaf rule says is, if such a situation is quite normal, that either of the carbon will have equal number of, either of the carbon has like alkene, basically the alkene those formed, will have same number of alkyl group. Right in this one is one of the carbon, this carbon has two alkyl, two carbon being attached with it, or we also call it or three carbon, like one, two, and three carbon being attached with this. But this carbon has only one carbon being attached with it. The second case, what I can show you is this carbon has one, two, and three carbon in linkage. And again, this carbon has one and two carbon in linkage. This is also linked with two other carbon atom, one and two. So the Sedgwick rule says that go for the product or the product which has more number of alkyl group. The preferred product is an alkene that has a greater number of alkyl group attached to the double bonded carbon atom. So that is what the rule says. Preferred product चाहिँ कुन हुन्छ त जहिले पनि preferred product चाहिँ यस्तो alkene जुनमा चाहिँ double bond मा चाहिँ बढी carbon number सँग attached भएको alkyl ग्रुपहरू छन् like is alkene which has there should be alkene but that has the greater number of alkyl group attached to the double bonded carbon atom. So this is the rule. What it says, alkene that has greater number of alkyl group attached to attached to the double bonded carbon atom. So the double bonded carbon atom has in this situation, this double bonded carbon atom has three alkyl group, and this double bonded carbon atom has only one alkyl group. And this one has two alkyl group, and this one has three alkyl group. So this one will be the preferred product. That is what Sedgwick rule says us. Let's move on for the next one. That is, I think we were having the reaction. Okay, well, let me clear you over here only. The student basically have confusion in alcoholic KOH and aqueous KOH. So if there is aqueous, the meaning of aqueous is in water. If we have potassium hydroxide solution in water or aqueous condition, and if I am treating it with alkyl halide, again the product will not be this. I mean, if I have same thing like CH3, same situation, CH2, C, CH3, CH3, and here I have a Br group, right? So in this again I'm treating it with KOH or potassium hydroxide, but in aqueous condition. So this time the product will not be same as before. Before it was alcoholic KOH and now it is aqueous KOH. So the situation, this is aqueous and this is alcoholic. They are different. Sorry, this one. This one is alcoholic. Okay. So aqueous KOH, what will happen is this will go for hydrolysis. The bromine group will come out. This one will break as K plus and OH minus. And this K will take the Br and the OH will take right the position of this in order to form the hydroxyl group. And the product those formed will be CH3, CH2, C. The product will be something like this. CH3, CH2, C, CH3, CH3, and here will be OH. So basically what you need to understand is when you treat it with aqueous KOH, hydroxyl group will come. And when you treat it with alcoholic KOH at the time, alkene will be formed. So don't get confused in aqueous potassium hydroxide and alcoholic potassium hydroxide. The product those formed will be different. In this situation, you will have hydroxy group or alcohol. And in alcoholic KOH, you will have alkene or there will be dehydrohallucination reaction. Let's move on for the next one, that is the Wurtz reaction. Most common and known reaction, I believe, that you people might be knowing about. Wurtz reaction. Wurtz reaction. So, what is the necessary condition for Wurtz reaction to take place? So, the necessary condition is there need to be alkyl halide group. So what we need is we need alkyl halide. We need alkyl halide. How many molecules? Two molecules. And along with it, we need sodium metal in the presence of dry ether. In the presence of dry ether. That's a necessary condition. And the product formed will have double the number of carbon atom as that of the reactant. And if you are heating it in the presence of dry ether, it will generally form the alkyl group. Like if I have something like this, let me take an example. If I have Rx and if I'm treating it with two molecule of Rx and if I'm treating it with two molecules of Na in the presence of, here will be the formation of alkene. And if I'm treating it with the presence of dry ether and heating it, what will it form? It will form double the number of alkyl group. If you have one carbon in the product, you will have two carbon. If you have two carbon in the reactant, in the product you will have four carbon. If you will have three, the product will have six. So exactly the number of carbon will be double, along with the liberation of two molecules of NaX. Let me show you with some example. I have CH3, CH2, Br, and I already mentioned, let me take two molecules, and I have two molecules of Na again. And I'm again taking one more molecule of CH3, CH2, and a Br, sorry, CH2 and a Br. Then, so what will exactly happen in this is this Br and this 2Na will liberate out. And what was the condition for the reaction to take place? So we need to heat it in the presence of dry ether. Now what will exactly happen is this two alkyl group and this alkyl group will attach together and the product will be CH3, CH2, CH2, CH3 along with the liberation of two molecules of NaBr. And where the student basically make mistake is this type of easy questions can be done. But sometimes people will have query like the product or the question is given. Always remember the confusing question will be right in front of you during the examination. So if you will have something like this, CH3, CH, CH3, and here you have a halide group like Cl, and its two molecule has been given, and you need to treat it with two molecules of Na, right? So what will be your product in the presence of dry ether? Dry ether and heat. So what you need to put in mind is what is a molecule right now? Let me explain you downside. So what I mentioned is let me mark it like this CH3, CH, CH3. Yeah. Here I have a Cl group. वापस से मैंने दूसरा वाला लिखा CH3, CH, CH3 and here I have a chlorine group. And here let me take two molecules of Na. What will happen is this Cl will come with this two Na group. Okay. And the molecule those formed will look something like this. According to me, it will be like this CH3, CH, CH3, and the bond will join here CH, CH3, and CH3. So your product will look something like this. Or it can also be made like in order to confuse you people, the answer is same. Even if you will make it like this, it will not have any changes. Or it can be written as CH3, CH, single bond, CH, CH3, and one of the CH3 will be shown here, and the other CH3 will be shown here. So it can be represented, the answer is same. Okay? So this is Roche reaction. If you will have alkyl halide in the presence of Na and dry ether, it will form double the molecule of Na along with the liberation of NaX. Now, lastly, let's move on for some of the chemical reactions where basically students get confused. So action of alkyl halide with NaCN KCN, action of action of alkyl halide halide with NaCN KCN and AgCN. So what will be the product basically in this situation? So if I have an alkyl halide group like Rx group, then and if I'm treating it with NaCN, what will exactly form? And they are alcoholic. They are alcoholic. What will basically form is here will be the breakage, right? The Na will take the X group to form NaX, and the Cn will go and attach right in the R group. It will form RCN, and there will be the formation of NaX. So Cn is basically what we call cyanide. So we can call it alkyl cyanide, or we can also call it alkyl nitrile. Then same goes with again if I have Rx group and if I have KCN, again if it's alcoholic, it will give you the product that is CH3, CH2 and CN along with the liberation of KX group. So again you have, what do we have over, sorry, there will be RCN. Okay, again you have your product as, again you will have here also you have alkyl nitrile. Here also you have alkyl nitrile or alkyl cyanide. But the question comes when you have again Rx group and if you're treating it with AgCN, AgCN, and again it's alcoholic. But this time the product will not be alkyl nitrile. This time the product will be alkyl isonitrile. That is, again the bond will break. But this time the carbon will not attach with alkyl group. This time the nitrogen will attach with the alkyl group. That means the product is gonna be, or the product will be RNC along with the liberation of AZX. So what I mentioned right over here is in the presence of AgCN, the product is going to be alkyl isonitrile. What will be there? Alkyl isonitrile. Alkyl isonitrile or alkyl isocyanide, whatever you call it. Okay. So here your product is RNC, but here your product was RCN. अच्छा, तो आपको याद क्या रखना है कि NaCN के साथ और KCN के साथ क्या देता है, RCN देता है. पर अगर हमारे पास AgCN है तो उस टाइम पे हमारा प्रोडक्ट क्या आ जाएगा, RNC आ जाएगा, अल्काइल आइसोनाइट्राइल आ जाएगा. ठीक है, या अल्काइल आइसोसाइनाइड आएगा. तो कंफ्यूज नहीं होना है, इस सिचुएशन पे प्रोडक्ट क्या आएगा वो ध्यान रखना है. Next, same goes with alkyl halide. If I have again alkyl halide group, sorry, reaction of alkyl halide with reaction of alkyl halide with alkyl halide with NaNO2, KNO2 and AgNO2. AgNO2. So again, the same criteria, situation, something is somehow same. If I have alkyl halide group and if you're treating it with NaNO2, what will happen is again the Na will take the halide and the NO2, basically it is also an ambident ligand. Ambident ligand is a ligand which can make double connection or which have two site of connection with the alkyl group. The product will be R and there will be O, N, double bond O, along with the liberation of NaX. That means the product those formed as what we call alkyl nitrite. We'll call it alkyl alkyl nitrite. Again, if I am treating it with Rx with KNO2, the product will be R O N double bond O along with the formation of KX. Again, we will have alkyl nitrite. But if I have AgNO2 right there again if we have alkyl halide and if we are treating it with AgNO2, at this situation, the product is gonna be R and the link point with the carbon will be N, double bond O, and a coordinate covalent bond O. And we also call it, along with the liberation of AZI, we call it nitroalkane. Nitroalkane. So do not get confused. If you have NaNO2, KNO2, your product will be nitrite. Okay. But if you have AgNO2, your product will be nitroalkane or the point of connection will be N. So this is what I think you need to remember. These are the confusing point basically. So NaNO2 and KNO2, they have your product as nitrite and AgNO2, you'll have product as nitroalkane. NaCN and KCN, you will have product as alkyl cyanide. And if you have AgCN, your product will be alkyl isonitrile or isocyanide RNC. And aqueous KOH and alcoholic KOH, if you will treat it with aqueous KOH, already mentioned above, aqueous KOH, you will have alcohol in the product. And if you will treat it with alcoholic KOH, you will have alkene or double bonded situation. So that's all about all this. So I'll be attaching right few questions in this video. Kindly do it. And if you'll be able to solve it out, click the pictures of the answer set and attach it right in the comment section. So here we have some questions related to the video that we have made. So you might have already gone through the entire video. Here you have a question that there is an organic compound. An organic compound having a molecular formula C3H7X. So the compound need to have three carbon, seven hydrogen, and a halogen group. Okay. So what it is saying is you need to give a proper sequence of reaction in order to convert primary haloalkane. इसको use करके आपको एक primary haloalkane बनाना है and same you need to make and you need to convert that primary haloalkane into secondary haloalkane. Okay, that's your question is. And whatever the secondary haloalkane you will find, if you will treat it with the Urge reaction, what will be the product? That's a question, right? Try to solve it if you will be able to do. Great. If not, I'll be making another video for by solving all these questions. Okay. Let me complete the second video of hello alkane and hello arene, and then I'll be doing the entire question together. I'll be making a video for the question solving. Okay. So second question you have that there is an unsaturated hydrocarbon. Unsaturated means double bonded or triple bonded. So we have molecular formula C3H6, so it need to be a double bonded. And it's saying that it undergoes Markovnikov rule to give A. So you need to add hydrogen halide HBr or HCl, and by following Markovnikov rule, this compound makes A. Compound A, you need to hydrolyze it with aqueous KOH, and it will yield B. The B is further treated with PbR3. So I have not spoken about PbR3. PbR3, what it does is the hydroxyl group, OH group, will be replaced by Br, and which it gives C, right? The C, which is further treated with AgCN in the alcoholic medium, I have already discussed, it will give D, and the D on last, lithium aluminum tetrahalide, this is a reducing agent. So basically, reducing agent means it will add certain number of hydrogen in it. LiAlH4 को काम की होता है, ये लेती certain number of hydrogen से double bond लाई replace करे ना, bond लाई replace करे, then से hydrogen लाई लेने काम करता है, right? And last reaction, I think you people can do it. So kindly solve it out, and if you will be able to solve it, attach it right in the comment section so that the friends who will not be able to solve it out will get help from it. Thank you.